So we have three charges at the corners of a equilateral triangle. So each side is 0.5 meters. And we're given the charges. Calculate the electric field at a point midway between the two charges on the x-axis. So we're focusing right here. Okay, so before I started recording, I explained this. I'm just going to explain it again. So look, this guy's positive, this guy's positive, this guy's negative. The problem starts with figuring out the directions of the electric field at the point we're focusing on, the midpoint on the x-axis. Oh, and by the way, what's the equation that applies here? If you're solving for the electric field at a distance from a big charge, the equation that applies is KQ over R squared. Notice that the charge is absolute valued. Because what is plus and minus in physics? The direction. Is the equation going to tell you which way the electric field is at the point you're focusing on? You actually have to look at the situation. So for example, all right, so let's call this guy charge 1. This will be charge 2. This one will be charge 3. So we got 1, 2, 3. So charge 1 is a positive charge. What do we know about the electric field for big positives? Do they go in or out? It goes out. Electric field goes out in all directions. Now what's the reason for that? Why does the electric field go out? Well, if you stuck a little positive guy near the big positive, which way does the little positive guy go? Out, right? The direction of the electric field is based on little positive. Which way does a little positive guy want to go? Okay, so at the point we're focusing on, down here, what's the electric field from charge 1 doing at this point? It's going like this. It's going out like that. Does that make sense? Okay. So I'm going to put a there. This represents E1. That's the electric field from charge 1. Okay, now go to charge 2. It's positive. Electric field is going out in all directions. But what's it doing at the point we're focusing on? It's going out to the right, like that. E2. All right, so we'll put. So this arrow here represents electric field from charge 2. All right, lastly, charge 3 is negative. The electric field for big negatives go in, because what would a little positive guy do? A little positive guy would go in to big negative. Okay, so the electric field from charge 3 at the point we're focusing on is going into the big negative. So basically, I mean, we could call this a free body diagram. It's not really a free body diagram, but let's just call it that. So here's what we got. We got E1 pointing down, and then we have E2 and E3 pointing to the right. So these are our directions. Okay, the next step, you got to calculate what each of these electric fields are. So we're going to need some distances here. So for example, we need to solve for this distance here, right? From charge 1 down to the point we're focusing on, how do we get that distance right there? Well, what's the hypotenuse? It's an equilateral triangle. So this hypotenuse here is 0.5. We have the angle, so we can solve for what this is. So this distance right there is going to be sine 60 times 0.5 meters, which comes out as 0.43301 meters. Hey guys, don't round these numbers. A very common mistake is to round, like if you were to round that to 0.4, you're going to get rounding error. So just use the whole number. Okay, so I would take it out about that far. So this is the distance right there, from charge 1 down to the point we're focusing on. What's this distance going to be in here? What's that distance? That's 0.25. Same thing with this distance over here, 0.25. All right, so calculating E1, E2, and E3. So we're using this equation right here. So it's going to go 9 times 10 to the 9th Newton meter squared over Coulomb squared, right? That's K. All right, so starting with charge 1, that's going to be 3 times 10 to the negative 9, which is kind of nice because why? 10 to the 9th and 10 to the negative 9th just cancel. Okay, so the distance for charge 1 is 0.43301 meter squared. So when you punch that in, you get 144 Newton per Coulomb. All right, electric field 2. 9 times 10 to the 9th Newton meter squared over Coulomb squared. Charge 2 is 8 times 10 to the negative 9. And then the distance here is 0.25, right? This distance in here, it's half of the side of the triangle, which is, so the side of the triangle is 0.5, so half that's 0.25. Make sure you square it. I can't tell you how common it is where kids forget to square. You gotta square your distances, because that's what the equation says. All right, so this comes out as 1,152 newtons per coulomb. And then lastly, 9 times 10 to the 9th Newton meter squared over Coulomb squared. 5 times 10 to the negative 9, 0.25 squared. So then this comes out as 720. Okay, so we've calculated each of the electric fields. Okay, so we now have, so E1 right here is 144 Newton per Coulomb. E2 is 1,152 Newtons per Coulomb. And then E3 is 720 Newtons per Coulomb. Okay, we now need to figure out total X and total Y. Is this an easy situation or a hard situation? It's easy. What makes this easy? There's no angles. So for example, what's the total X going to be? We're going to add these two together. E2 and E3, you add those together, that's going to be the total X. So that works out as 1,872. What's the total Y? 144. The answer that we're looking for is the hypotenuse. That's going to be E net, the total electric field. So you do Pythagorean theorem, and it comes out as 1,877 newtons per coulomb, but then you also want to get the angle because it's a vector. So to get that angle, theta is tangent inverse, opposite, over adjacent. So this comes out as 4.4 degrees. So the final answer is, the total electric field from those three charges at the midpoint of the base is 1,877 newtons per coulomb, 4.4 degrees where? Look at, you got X, Y, it's pointing that way, right? How would you describe that angle? Below the positive x-axis. Okay, any questions? Chapter 15 is time consuming. Very few of the problems are like super quick where you're just like, oh, done. A lot of the problems are like this. So anyway.